All right, today we're going to do a little bit of review, talk about supersaturated solutions again real quick, and then move on and talk about hygroscopic molecules, and then how to calculate molarity and how to calculate dilution problems. And so right now this is a solution right here of sodium sulfate. It's not totally dissolved, unfortunately, so hopefully this is going to work. But anyways, what I've done is I heated up the solution so that the water inside of it would absorb the maximum amount of sodium sulfate, and then if you cool it down, it will keep the sodium sulfate dissolved until you disturb it. So some of it is already precipitated out, but hopefully the rest of it, when I disturb it, it will leave the solution, because right now, once it cools back down, it doesn't have as much space between the water molecules anymore, and it can't hold as much salt. And so hopefully that's what we'll see, is that it'll precipitate out from this supersaturated solution. So there's a disc in here. I'm just gonna break that disc, and you can see there it is. It is actually, all that salt now is leaving the solution, and since it's now sticking together, it actually releases heat. That's why it says the heat solution. So right now it's actually really warm. It's a hand warmer is what it is, because it'll stay warm for a while. Because remember, when those salt molecules go from being in a liquid to sticking together as a solid, they're slowing down, they release heat to the surroundings, and so that's why it's actually heating things up around it. And then next thing we're going to look at is hygroscopic molecules. And so this is some sodium polyacrylate is what this is. Let me try to change it here, angle on it a little bit. So there's some sodium polyacrylate, and what I'm going to do, and it's a hygroscopic molecule. Now, the thing is, what are hygroscopic molecules? They're molecules that absorb water. And so here's some examples. You'll see these things, these little packets here. It says silica gel. Do not eat them. And the reason is they're toxic for one, but what they're doing is they're hygroscopic molecules, so they absorb water. So you actually find these in boxes of shoes, beef jerky, vitamin boxes. I just got this one actually with the beakers that I just ordered. And again, so they're hygroscopic molecules. They absorb lots of water. And in the desert of the Atacama Desert in Chile is actually the driest place on earth. They get like 1/10 of an inch of rain a year, but there's some salt, blocks of salt and stuff that are there, and if they cut them open, you'll see algae growing inside of them, and it's because the salt absorbs water, and so the salt is hygroscopic, so it absorbs just the water from the atmosphere, and it allows algae to be able to grow, because you wouldn't think anything would be able to live in a climate that's actually that dry. So it is the hygroscopic salt that's in all the dirt there that allows some algae to grow. So again, this is sodium polyacrylate, and it is hygroscopic as well. So add a little water to it, and you can see there that it's absorbing the water. And what's happening there is actually the process of osmosis. So it's a hygroscopic molecule. It's a polymer that's got sodium in it, and the sodium actually wants to leave the compound and go into the water, and the water then goes in and replaces it. So that's why they absorb so much water. And so you can see now, it looks like snow there. It doesn't even really stick to your hands or whatever. So again, they call it poly snow. So there's an example of one type of polymer that's super absorbent. Again, it is hygroscopic. Here's another one, and this one, you'll see it doesn't actually make the snow type thing there, but it does absorb all the water. It can absorb about 800 times its mass in water, and it's again for the same reason though. It's the sodium in it that is being replaced by water. The sodium again wants to move into the water. The water goes in to replace it into the polymer, and so that it absorbs it. And so this is what they use this in diapers, stuff like that, where they need to absorb a lot of water. And anyway, so those are hygroscopic molecules. So here's where I'm at in the notes. And so that's where we left off last time, it's page 8 there. So one of the things, and we'll look at too, and we'll change this around a little bit here. So the idea of hydration, what are hydrated molecules as well. And we did a lab earlier in the year, copper sulfate pentahydrate. Again, it's a molecule that's attracted to water. That means that copper sulfate is surrounded by 5 water molecules. This is actually what was just in the hand warmer that we're looking at, sodium sulfate pentahydrate. So those are hydrates, or molecules that are surrounded by water molecules, and they're stable that way. All right. So the other thing, before we move on to what we're doing today, we can talk about also types of solution, or types of mixtures that look like they are actually solutions, which would be homogeneous mixtures, but they're not, and they're called suspensions and colloids. And a suspension, the difference between a suspension and colloid is a matter of particle size. Suspensions have larger particles than colloids. Colloids will have a tendency, they have intermediate sized particles, they have a tendency to stay suspended for a long period of time. Kind of like milk and water would be a good example there. And a suspension has larger particles that will actually settle out. It's like if you get some dirt, throw some dirt and water and mix it up really well. At first it looks like they're evenly mixed, but over time it's going to settle out because the particles are larger. And they said that colloids actually exhibit what's called the Tyndall effect. And the Tyndall effect is when you shine light through something, it scatters the light. So if you shine a light through water, the light won't be scattered, but you put a little milk in there with it, those larger particles will scatter the light. And again, that's called the Tyndall effect. So it's just a way to identify a colloid. All right. Let's see. So let's talk about molarity today, how to calculate molarity. And molarity is just our way of talking about the concentration of a solution. It is the amount of solute over the total amount of solution itself. So again, here's how we calculate the concentration of something. The higher the molarity, if we say it's a 1 molar solution of salt or a 2 molar solution of salt, the higher the molarity, the more concentrated it is, obviously. So again, when we talk about concentration, we're going to talk about molarity. Anyways, so let me show you how to calculate this. So let's calculate the molarity when 3 moles of solute dissolved in enough water to make a 2-liter solution. So we'll always start off with a really simple, easy problem, and then move on to problems that are a little tougher from there. So first of all, again, here's our equation we use. So we got 3.0 moles of solute, and it's in a 2.0 liter solution. And then to get the molarity, we'll just divide the two, and you get 1.5. And we use capital M for molarity. So that's what that means. That is moles per liter. So in that particular solution, you have 1.5 moles of solute in every liter of solution. So that's telling us the concentration. The next problem, so the solution contains 17.0 grams of sodium chloride in a 1200 milliliter solution. What is the molarity? Okay, the solute is in grams, but it needs to be in moles. And the solution is in milliliters, and it needs to be in liters. So we have to convert both of them to do this problem. Remember, it's always easy to convert from grams to moles. We've been doing that all year. So you got 17.0 grams of sodium chloride, which is NaCl. We're going to go to moles of NaCl over grams of NaCl. And let's see, I think I've got it worked out somewhere here. Yeah, the sodium chloride, you look it up on the periodic table, it weighs 58.443 grams. So it would be 17 divided by 58.443 with sig figs. That is 0.291 moles. And then milliliters to liters, I'll set this up over here, 1200 milliliters. If you're going to convert that to liters over milliliters, 1 liter is 1,000 milliliters, so it's 1,200 divided by 12, which gets us 1.2 liters. Again, that's 2 sig figs there. So again, that's moles divided by liters will get us the molarity. So 0.291 divided by 1.2, and the molarity now is 0.24. And again, capital M, remember that means moles over liters. It is concentration. And then the last one for molarity problem says how many grams of sodium chloride are needed to prepare 275 milliliters of a 0.2 molar solution of NaCl. So what we have now, so what we're going to do, when they're always asking for grams, we're going to solve for moles, and then we'll convert that to grams when we're done. So what we have now is we've got a 0.20 molar solution, so that's the molarity. Remember, molarity is equal to moles, which is what we're going to solve for, over liters. And 275 milliliters, again, you divide that by 1,000 to convert that to liters would be 2.275 liters, and then solve for x. This is a proportion, set it up, cross multiply. X is equal to 0.2 times 0.275, so 0.2 times 275 is 0.055, and with 3 sig figs, so we need to say it's 0.0550 moles of NaCl. It's NaCl there, but they wanted the answer in grams. They want to know how many grams of solute we needed to make this, to prepare this solution. So again, we're going to go to grams of NaCl over moles of NaCl. 1 mole, again, 58.443 grams. And then multiply across, so 0.055 times 58.443. And we get, with sig figs, 3.21 grams of NaCl. So what does all that mean? It means if you put 3.21 grams of NaCl and 275 milliliters of water, the concentration now would be what we were looking for, 0.2 molar. Again, that's moles per liter. All right, last thing, look at dilution problems. And it's something that I work on all the time, because when we're in a typical year, when we're doing a lot of labs, we need a certain concentration that we can't get from the company. The company sells us all of our like acids at a specific concentration. In other words, every time I buy hydrochloric acid from them, it's 12 molar. But I can't let students in class have 12 molar hydrochloric acid because it's actually, that's too concentrated, it's dangerous. So we always have to dilute them. And so what we know from, when we're doing a dilution problem, you have to understand the molarity and volume of your initial solution will equal the molarity and volume of change of a new solution, because if you're diluting something, all you're doing is adding water. So you're not changing the number of moles you have. Remember, the equation for molarity is equal to moles over liter. We can rearrange this and say that the volume we have in liters times molarity, because remember, that is moles over liters, so it cancels out. That will give us the moles that we have. So we can say that, because this is volume and that's molarity, obviously, we can say that the initial molarity and volume will equal the change in molarity and volume. Again, look at it common sense wise. Let's say you put 1 mole of salt, 1 mole of salt in 1 liter of water. And so you have 1 mole, and so the molarity is 1 mole per liter, so the molarity would be 1. So if we said, how many moles do we have in this case? We have 1 liter of solution, and again, molarity is moles per liter, so that would be 1 as well. We have 1 mole of salt. Well, what if we added another liter of water, though? So you add another liter of H2O. So now we have 2 total liters, but now the molarity would be cut in half, because now it's 1 mole for 2 liters, or the molarity is 0.5, but the molarity times the volume will always equal the number of moles you have. So since when you're making a dilution, you're just adding water, we can determine how much water we need to make any particular type concentration of solution we want. So that's why we can use, that was kind of a long version of why we can use that equation. So I'm just pointing that out, why we can use it. So here you go. So it says how many milliliters of concentrated stock solution, again, like I say, when I order hydrochloric acid, it's always 12 molar, is needed to prepare 250 milliliters of a 1.75 molar solution. So again, we know the initial molarity that we're working with is 12 molar. We want to know how much of that we need to make the stock solution. And again, they want it to be 1.75 molar. And we need 250 milliliters of that. Again, you just multiply across and divide. So we'll do that real quick. So we got let's see, we end up with 36.5 milliliters of stock solution. Now you do need to, I need to explain, it doesn't really tell you what actually needs to be done there, but let me explain what I would do to make this. So I would take my stock solution with a graduated cylinder here, take a graduated cylinder, and what I'm going to do is I'm going to take the stock solution that's 12 ml, I'm going to pour 36.5 milliliters into that graduated cylinder. And then all I'm going to do then is I'm going to pour water in here. And so then I add water to it until it gets up to 250 milliliters. And once you've done that, that's going to be your new, because all I've done is dilute it. And then the new concentration is what I was looking for, 1.75 molar. And let's see, that's it. This part of the page here is just explaining again what I was talking about with why we can do dilution problems, and you don't have to worry about molality. We're not going to do that. So good luck. You've got a Go formula to work on.